Modern quantum mechanics rests on two baffling phenomena: non-locality, particles reacting instantly across distances, and retrocausality, effects preceding their causes. The accepted explanations for these behaviors, famously dubbed spooky action at a distance and backward-in-time causation, explicitly break the classical rules of cause and effect. If data truly transmits faster than the speed of light to coordinate these states, it shatters the strict limits set by general relativity. These contradictions survive in physics because of an entrenched mid-century assumption: the idea that taking a measurement is merely a passive extraction of mathematical information. But every actual measurement in a laboratory requires physical equipment, consuming power and exchanging energy with the surrounding environment. To resolve these violations of causality, we have to discard the idea of abstract mathematical updates and redefine measurement as a physical thermodynamic transaction. This physical approach is called Observational Dynamics, or OD. It formalizes every act of observation as a direct entropy-energy transformation. This equation details the transformation. When observed, a quantum system physically discharges its potential energy, E sub O, into the environment. The right side dictates this discharge rate. Specifically, the environment's impedance and temperature strictly limit how fast that potential flows. This localized depletion of energy is the actual physical mechanism that forces a quantum superposition to instantly collapse. Observation acts as a synchronization event between the system and the observer, restricted by the finite bandwidth of this thermodynamic cycle. Standard quantum mechanics ignores this, assuming an observer with infinite capacity that updates states instantly across the universe without any energetic cost. By binding observation to this strict thermodynamic limit, the seemingly magical paradoxes of entanglement and the delayed choice erasure completely vanish. We start by redefining superposition. Instead of a probability wave, OD defines it as a high-capacity reservoir of potential energy. Taking a measurement closes a thermodynamic circuit. The moment it connects, the reservoir drains through the environment's impedance. This rapid discharge strips the system of its internal transform degrees of freedom. Stripped of that coherence, the drain system is physically forced to drop into a determinate static coordinate point. As long as that observer remains connected, energy continuously dissipates, making the state change completely irreversible. Quantum collapse is simply the localized depletion of potential energy against environmental impedance. Understanding this specific mechanism solves the entanglement problem. Under observational dynamics, entangled particles do not require invisible, non-local connections. Because they previously interacted, their independent energies fuse into a single thermodynamic reservoir. These particles can drift light years apart, but their energy remains bound to that single mathematical capacity. When an observer measures particle A, that specific local energy fraction drains to zero as the thermodynamic circuit closes. Because total potential must be strictly conserved, depleting energy on one side forces an instant update to the other. Absolutely no information, particle or faster-than-light signal travels across the empty space between them. Particle B's state changes instantly because the shared mathematical coupling is perturbed, not because a physical message crossed the gap. This relies entirely on robust local mathematical conservation, eliminating the need for a mystical, spooky action narrative. Non-locality is an illusion caused by ignoring this shared thermodynamic coupling.
Entanglement is fully explained by local energy conservation. In the delayed choice quantum erasure experiment, an unmeasured photon retains its potential energy, allowing it to create a complex interference pattern. When researchers insert a detector to record the photon's path, they introduce a severe thermodynamic drain on that potential. Depleted of coherence, the system drops into a determinate state, leaving a classical scatterplot. This leads to the famous paradox. When researchers delete the path data after the fact, the interference pattern returns, leading to claims that the deletion retroactively rewrites the particle's past. The reality is strictly thermodynamic. Destroying the path data physically decouples the measurement apparatus from the particle. Breaking that circuit removes environmental impedance, triggering the replenishment potential variable to refill the photon's reservoir in real time. With its thermodynamic potential restored, the system regains the capacity to support multiple transform degrees of freedom, allowing the interference pattern to re-cohere. This is a straightforward, forward-moving energetic recovery. It requires zero backward-in-time causation. There is no time travel in quantum mechanics. There is only physical energy depletion, followed by thermodynamic replenishment in the present. The principle of observational equivalence hinges on a mathematical reality. A classical object we cannot see maintains the same undisturbed potential energy as a quantum particle. If the impedance between us is high enough to prevent any energy discharge, the equations governing a single atom and a distant mone become identical. Because there is no thermodynamic connection, those macro-scale objects retain their transformed degrees of freedom just like a particle in superposition. This proves that the observer, by closing that circuit, is the active source of entropy in the system. To maintain internal order, the observer radiates entropy outwards, discharging into their light cone. This thermodynamic discharge requires a physical point of origin. To radiate entropy, the observer must occupy a specific coordinate as a distinct low-entropy zone against the environment. In a circuit, energy cannot flow without a source terminal. In this thermodynamic model, the observer acts as the low-entropy pole of a dipole, connected to the high-entropy environment. Standard physics attempts to calculate the universe as if information can be collected without a physical terminal, ignoring the necessary energetic weight of the observer. This localized spatial connection is what we recognize as physical embodiment. It is a strict thermodynamic requirement for the act of observation itself.
Standard quantum mechanics generates paradoxes because it treats the observer as an entity existing outside the physical system, ignoring the energetic cost of data extraction. Entanglement is the mathematical sharing of a localized potential energy reservoir, and measurement is its physical discharge. The quantum erasure is the physical decoupling and replenishment of that same energy, resetting the system's capacity for coherence in the present. And when we test these thermodynamics at a cosmic scale, the observational limits of our universe perfectly match this model's predictions. Observation is the process of light carrying that energetic discharge away from a system. Because this discharge forces the drop from potential to determinism, the reach of light defines the boundary of a determinate reality. Mathematics cannot distinguish between a quantum state and an unobserved classical state. The universe is rendered determinate strictly through the thermodynamic class of observation.